So, good time of the day. Welcome and thank you for joining this education and training webinar. It's the number 105 in this series, and it will present a German perspective on the science for the safe disposal of nuclear waste. First, I'll go through a few housekeeping moments. So please use the listen through your computer option to have the best sound quality. If you have any issues, we encourage you to search for support on the website of the Zoom platform. And if you have a question, and I'll come to that on the next slide, but if you have a question during the webinar, please ask it directly using the question and answer pane on your screen. The questions will be taken at the end of the presentation. After this webinar, the recording and the presentation of the webinar will be posted on the GIF public website. And you should receive a survey at the end or on the next day after the webinar. And if you have a moment, please take this survey to help us improve this series. So regarding the Q&A, you have at the bottom of your screen, as you can see here on the screenshots, in the different options, you have the Q&A button. If you click on it, you will have a pop-up that will come out. And there you can type your question and send it. And the panelists and the organizers will see your question, and all the questions will be taken at the end of the webinar, but you can ask them as they come to you during the presentation. I would like now to introduce our moderator for today's session. Dr. Patricia Pavier will moderate this session. She's the National Technical Director of the Molten Salt Reactor Program for the US Department of Energy, Office of Nuclear Energy. She's been an active member of the GIF Education and Training Working Group since the inception of this group, and she was actually the first chair of the Education and Training Working Group. She's now the webinar lead for the ETWG, the Education and Training Working Group of GIF. She has been instrumental in establishing the present series of webinars and keeps it flourishing with the energy and enthusiasm she puts in it. She will facilitate the webinar and the follow-up Q&A session today, and I will now let her introduce our speakers for today.
Thank you very much, Alexei. Good morning, everyone. It's a pleasure to be here today. We have two presenters from the Karlsruhe Institute of Technology, INE, which is the department for the Institute for Nuclear Waste Disposal, Dr. Francesca Quinto and Dr. Frank Heberling. Francesca is deputy head of the radionuclide specialization in analytics from KIT-INE after receiving her PhD in novel physics methodologies applied to environmental research at the Seconda Università degli Studi di Napoli. She was for 1 year at the Vera Laboratory of the University of Vienna in Austria, and afterwards a postdoc at the Joint Research Center Institute for Transuranium Elements in Karlsruhe. Her research focuses on ultratrace analysis with accelerator mass spectrometry and radionuclide migration in crystalline and clay rocks. She's a member of the German delegation of the Crystalline Club of the Nuclear Energy Agency and an experiment team delegate for the International Steering Committee of the Grimsel test site. Dr. Frank Heberling is deputy head of the Radioactive Waste and Barriers in Repository at KIT-INE and is a lecturer in applied geoscience at KIT. He is leading a research group focusing on investigation of radionuclide migration in waste disposal barriers. He received his PhD in geochemistry and mineralogy at KIT. His research focuses on the interactions of radionuclides with mineral phases, including synchrotron studies and thermodynamics modeling, as well as diffusion processes of radionuclides in clay materials. He's a member of the German delegation of the Clay Club of the Nuclear Energy Agency. So before I give you the floor, I would like to first thank you, of course, for volunteering to give this webinar. And I invited you because I think it is very important, even though we are with the GIF, a Gen 4 International Forum, focusing on nuclear reactors. It's very important to think about the entire fuel cycle, the waste, and where the waste goes. Every nuclear reactors will produce waste, so we need to think about where do they go, what is this waste, and what is the geology and the chemistry of these waste under repository conditions. So I'm very happy to have you here. I worked at INE a long time ago, for 4 years. I learned a lot, and I'm really delighted to listen to your webinar. So Francesca and Frank, I give you the floor now. Thank you very much.
Yeah, thank you very much, Patricia, for this nice introduction. My name is Frank Heberling, as you may have guessed by the voice. I will start now the presentation. And so the title we gave this presentation is Science for the Safe Disposal of Nuclear Waste, a German Perspective. And to come into this topic, I first would like to present you like the framework that we are working in, or the boundary conditions in Germany, as may also be like controversially discussed in the Gen 4 community. We have a phase out of nuclear energy in Germany, and this actually sets pretty well constrained boundary conditions to our nuclear waste program. And also since a few years, we have a site selection procedure also fixed by German law, where it's well regulated how we search for a site for a deep geological repository, which I want to introduce. Then finally coming to our institute, the Institute for Nuclear Waste Disposal here in Karlsruhe in the south of Germany. And then basically we will have like 2 research highlights, as we call it. First, as I will talk already for a while during the introduction, I will have a relatively short insight only into some research I'm doing on clay rocks specifically, which are a potential host rock in Germany. And then I will hand over to Francesca, who will give like a more in-depth insight into her research, which is directed towards radionuclide waste repositories in granitic rocks and colloidal transport in this rock type. Okay, but let me directly jump in and present you some of what's the nuclear waste inventory in Germany that we are dealing with. So concerning the high-level waste, inventories are listed here. Basically, we have a Federal Ministry for Environment who has the duty to do the bookkeeping for the nuclear inventory. And actually, you see many of the spent fuel, which was used for energy production, is still located close to the nuclear power plants. So more than 5,000 fuel assemblies still stored really in the cooling ponds of nuclear power plants, the status of end of 23 here. And this is an overall activity of more than 10 to the 19 becquerel. Then some of it is already in dry storage, or with 23,000 fuel assemblies, and only actually relatively few containers have already been moved to interim storage sites in Ahaus, Gorleben, and Nord. That's about 80 containers which are deposited there. And the whole, which is already like in interim storage, either near the power plants or in the interim storage facilities, is also a little bit more than 10 to the 20 becquerels. And as you may have heard, in Germany, we have no own like reprocessing program. But some of the fuel had been reprocessed, mostly in France. And now we retrieved the vitrified waste, which also must go to a final repository in Germany. This is more than 3,000 cocktails, which are at the moment stored in containers in the interim storage site in Gorleben, Nord, and Biblis. Besides this, we have a minor inventory from demonstration and research reactors, which is relatively little concerning the total amount of this waste, However, it's often quite special waste, and therefore it also deserves some special attention. And some, for example, there is from Jülich, you may have heard, they have these graphite ball reactors where there is very graphite-rich waste and things like this, which are really special also when it comes to how to dispose them. And so, as I said, after the phase out, and we have these well-defined amounts of nuclear waste, and the total expected volume is like 30,000 cubic meters. So if you think of a waste repository, that's actually not that much. So if you imagine like a swimming pool, 50 meters length, 20 meters width, would be like 30 meters deep, and then you could put the whole waste there. So like a big, yeah, big hall. And so this would be the high level waste that we are dealing with. And of course, this is a relatively small volume, but it's more than 99% of the activity actually that has to be disposed. And then with a much, much lower activity inventory, but with a much higher total volume, we have also a big inventory of low and intermediate level wastes. And here actually, it's distinguished between waste, which is already foreseen for a certain waste disposal site, which is called the site Konrad. Also here in the lower right, you see a map. So there are some points here on this map. One is the waste disposal site for low and intermediate level waste in Konrad, which is here. And the other spots are Asse, which I will talk about later. So it's more or less a legacy site. Morsleben, which is the nuclear waste repository from the German Democratic Republic, so before the reunification of Germany. And actually Gorleben plays no more role in the site selection. It's just at the moment an interim storage site. So, and with this waste that is supposed to go to Konrad, like I said, it has a relatively low total activity inventory. It's actually very diverse waste, from waste that comes from medicine to waste that comes from research facilities like here at KIT, till to the waste that comes from decontamination and decommissioning activities in nuclear power plants. And so foreseen for Konrad is a total volume of 300,000 cubic meters, so like an order of magnitude more than the high-level waste. And then there is also a large amount of waste which is actually already known that it will not be admitted or not fit into the repository in Konrad. And there is which is in Germany kind of famous, the Asse 2 salt mine. So this was a former salt mine which had been exploited quite extensively. And then it has been used like a research facility for waste disposal, and quite an amount of waste has been disposed there. But now they have problems with water inflow. So actually the current idea is to retrieve all of these waste and then to put it into a new low and intermediate waste level waste repository. Then there are also some waste from previous uranium enrichment processes, which sum up to about 100,000 cubic meter, and some further waste, which are not really specified. So it's like, again, about the same amount that will have to be stored in some repository, which is not yet even found. And this is also when we talk about site selection, we mostly talk about nuclear waste repository site for high-level waste, because this is the biggest concern. But actually, it's also an option that this low and intermediate level wastes might be stored at the same place, not directly in the same repository. There would have to be two separate buildings, but it could be in the same location. And like I said, since 2017, we have a Site Selection Act. So the German pronunciation is Standortauswahlgesetz. which regulates the search for a deep geological repository for high-level waste. And like I briefly mentioned, also opens this option to store the low or intermediate level waste at the same sites. And actually, for those who know a bit the situation in Germany, this was meant to be like a clean cut that after actually decades where there were heavy arguments between those who are in favor of nuclear energy and those who are against. And actually never, there was no conclusion found. And so with this law, actually a restart is attempted starting from a wide map of Germany to just have a very objective process, which will finally lead us to the repository site with the best possible safety. That's what is written in the law. And down here, what is sketched is the timeline and the separation of different phases and process steps in which this site selection is structured. So basically, it's structured in 3 phases. So the timeline goes here along the y-axis. Phase 1 is basically to look for sites based on already available data. In phase 2, there will be like above ground characterization of certain areas to look for their suitability. And then only in phase 3, there will actually be like underground research done to come to the final conclusion and the final suggestion of a site. And the thing which had been in the past often criticized is that there was no clear separation also between an operator and regulator. This has now been fixed with this law. So now we have the BGE, the German Bundesgesellschaft für Endlagerung, so federal company for waste disposal, which is now like our waste management organization. And as an opponent to BGE, there is the BASE, which is the regulator, the Bundesamt für die Sicherheit der nuklearen Entsorgung. So in English would be like Federal Agency for the Safety of Nuclear Waste Disposal. And basically, BASE is in charge of finding a site for a nuclear waste repository, and all the actions of BASE are then of BGE are controlled by BASE. And what is also important, finally, the decisions in each phase will be taken by the German Parliament. And what probably also plays a very important role is that also in the law, it's already defined how the public should be involved in the process. So this is here somehow symbolized by these 2 lines throughout all the process. There are clear steps at which the public needs to be involved and public concerns need to be heard and to be refed into the process. Yeah. And one, maybe the most important statement is the definition of what kind of waste storage we want at the back end of the nuclear fuel cycle. And there the law is relatively clear. So we have different categories, and actually this category A, this is like the site selection or the search that is actively pursued. And this clearly is the search for a deep geological repository. And as we are in Germany in a relatively lucky situation that we have all kinds of different potentially suitable rocks, we are currently still searching for a site which may be either in a clay rock, in a salt rock, or in a crystalline rock, meaning like a granitic rock or from the geological basement. Then there is a category B, as this is still like an open procedure. It might be that if in other countries there are some other options coming up for nuclear waste disposal, or nuclear waste repositories, that we also monitor these developments, and there is still the option to go to other types of waste repositories. And basically in this category B, there is only the deep borehole storage. This is, for example, something which is forwarded by some people in the US, and there is some research done. And so if this should advance very much, then it might be an option that we change towards this. And there is also a clear statement with this category C. There are many options which are not further considered, which is like everything that would keep the waste close to the surface, like permanent surface storage or long-term interim storage. As one of the fundamental concepts really is that future generations should not have to deal with the nuclear waste that was produced now by our generation or the generation before. And also with respect to like technological solutions, it's clearly stated in the law that partitioning or transmutation are no options in Germany. And then, I mean, there is a whole lot of other options which have been considered in the past, like dumping waste in the oceans or transferring to space or to Arctic ice sheets, which I think nobody is seriously considering anymore nowadays. But here it's also then black on white that they are clearly ruled out by this law. Here's the same timeline given again, but just maybe a little more detail. So this phase 1 with a investigation based on existing data is split it in 2 steps, and actually this first step is already finalized. So when BGE submitted a report of potentially suitable regions, which I will show soon. And now actually what they are doing, so basically what was done here, there are certain selection criteria like exclusion criteria, minimum standards, and then some more soft criteria for the geological assessment. And now basically these regions have been identified by applying the first 2 criteria, and now they are doing like preliminary safety analysis for every of these regions to assess which might be the safer region and to only keep the, let's say, safest regions in the search. And what is also clearly here at the end of the 3 phases, we should have a proposal for a site, and in the original law it was foreseen to be found in 2031. So that's only 6 years from now, and now I said we are now here in the first step of the first phase. So basically it has very quickly become clear that this is not a reasonable time frame. And so actually even the scientific service of the German parliament now already released a note that they think even 2070, so yeah, more than 50 or almost 50 years from now, would still be an optimistic estimation for a site selection. Optimistic means here they did not include the time frame for trials in the court when people like sue against this selection. Exactly. And yeah, so this first step, just to show you a little more details, like I said, we started with this white map of Germany. And then the first thing that had been done by BGE was to assemble all kinds of geoscientific data and then to apply these exclusion criteria. And basically all the dark spots that you see here would be the excluded regions. So what is excluded here is actually, for example, regions with volcanic activity. So we have some recent volcanoes here in the Eifel. Then seismic activity, so we do not really have anything like a San Andreas fault or so, but there is some very light or moderate seismicity along the Rhine River, which is here. Tectonic uplift mostly concerns the Alps here in the south of Bavaria. And many of the linear features you see here are actually fault zones, which have been active during the past 30,000 years. And therefore these regions are excluded. Then in the second step, everything that's white here was reassessed with respect to the minimum standards. So everywhere where there are suitable rocks below a certain depth, so the limit would be 300 meters. So the repository has to be at least 300 meters below the surface. The rock have to be at least 100 meters thick. have a low water permittivity, and the single regions need a certain area, so it's simply possible to build a repository there, just to mention a few of these criteria. And then after application of these criteria, basically this is the map that BGE came up with. So here these pinkish colors would be this crystalline rock, in purple is the clay, and then the blue spots are actually the regions with suitable salt rocks. And in here you cannot see it now, but there are some small blue spots, which would be like salt domes, as opposed to the salt layers, which are here in these light blue colors. And so actually also many experts have been really surprised that this is still more than 50% of the area of Germany. But well, so we're in the lucky situation, we have so much potentially suitable rock. But now actually in this second step, this is supposed to be also dramatically reduced. So much about the general background of Germany. Let me now introduce our institute here in Karlsruhe. Maybe now I talked too much about the waste management organizations, and just to make this clear, so we are independent of these and just are a public research institute, so we are not directly working for site selections or so. But on the other hand side, as part of the Helmholtz Association, most of our activities are embedded in a Helmholtz program, so nuclear waste management, safety and radiation research, NuSafe. And this also means that we have kind of a clear mission that all the research we do should somehow be useful for nuclear waste management. And in Germany, we're actually one of the few institutions that still has radiochemical lab facilities that allow to analyze or to make experiments with radioactive samples. And so with a licensing according to atomic law, we can work until the 10 to the 10th fold exemption limit. So this is really quite a lot of radioactivity. And we are also the only remaining facility with a shielded box line facility. So some colleagues are really doing experiments with small fragments of spent nuclear fuel. And because we work with radioactive samples, actually we cannot go with our samples to other institutes to do analysis. So we are really well equipped with analytical equipment and infrastructure. And as one example, we have run 2 beamline at the local synchrotron radiation source, which are specially dedicated to do X-ray spectroscopy on radioactive samples, and maybe more look into the future. As you will see later in more detail in Francesca's talk, we are also building now an accelerator mass spectroscopy facility, so we can analyze radioactive samples also down to the ultra trace levels. Yeah, so as I said, the KIT's mission is to provide research results relevant to nuclear waste management in Germany. And we have various topics from the decommissioning of nuclear facilities, so more like in the engineering departments, via prolonged interim storage, which is now especially a topic because we will not have a final repository in 2031, but the interim storage will be up to 40 years longer than this, until probably the main topic that we will talk about today, the research for the safe long-term disposal of nuclear waste in deep geological repositories. So this is one type of category. On the other hand side, we also do some really fundamental work, for example, with groups of really doing fundamental actinide spectroscopy or quantum chemistry, until really a very application-oriented work, as for example, some of the examples I will show for the nuclear waste disposal research, but also especially when you look at the engineering studies from the decommissioning groups. Besides the pure research, there is also further things that have to be done by the institute. For example, the knowledge transfer from the research institution to the waste management organization, for instance, or also because we have this long time frame of the repository site selection, we also need to maintain and to develop the competence to like attract new students and PhD students and postdocs to the field, so that we can make sure that there will be competent scientists working in the field of nuclear waste disposal. And now I talked a lot about Germany, but for sure I do not want to leave the impression that we work only in a German context, because most of the research work is actually performed in international collaborations in Europe and beyond. And so now finally coming to the research for the long-term disposal of nuclear waste, we mostly work on such a concept that we have a multi-barrier system, and we work on more or less all the compartments of such a multi-barrier system, going from the very inside, so where the waste is located, with work on high-level or low-level waste forms, to the canisters, canister corrosion. Then there is a backfill material, usually considered like a geotechnical barrier. Often it's bentonite or cement that we work on. Later I will show some study on bentonite. And then finally, the host rock as the final barrier, where we, as we still do not have a decision what will be the relevant host rock, we still work on all types of host rocks. What we will present today mostly goes into the direction of clay rocks or crystalline rock. And despite this, besides this very specific research on certain compartments, we also have some overarching studies, like for example, an aquatic chemistry group that works very generically on determining solubility constants for radionuclide on mostly actinide species, or also the aqueous speciation. So to develop thermodynamic models which could basically be applied to any type of repository, no matter if it's in salt rock or in crystalline rock. And also, of course, also overarching is that we strive to contribute somehow to the German site selection procedure with this knowledge that we gather. Yeah, so much introduction. Now, like I said, I will quickly introduce one part of the research that I'm mostly involved in, which is about radionuclide on radioactive waste disposal in clay host rocks. So where we usually aim at a multi-scale understanding of radionuclide diffusion and retention processes in this rock type, and also like in the whole multi-barrier system. Maybe the scenario which is considered is somehow sketched here on the right. Usually you could assume that you have the waste inside a steel container, then this bentonite. So this would be like the inner part, the so-called near field of a multi-barrier system, and then the host rock. But actually this is not like the situation where anything could happen. So I mean, here the container is still tight and nothing comes out. But there is a certain evolution over time. So as soon as there is groundwater intruding into the multi-barrier system, you will also have corrosion. And of course, these steel containers are very corrosion resistant, but usually it's assumed after about 10,000 years, you will have the failure of the first canisters. So some will be corroded to an extent that actually the water gets in contact with the waste, and the first radionuclides start to migrate out of your waste repository. In clay, that's mostly diffusion processes then, and that's what we are interested in. So how these radionuclides then interact with clay rocks, how they are transported. And what I'm presenting today is mostly the outcome of 2 PhD studies here. Unfortunately, the only picture I found of the 2 PhD students together was taken during the COVID-19 pandemic. So both are wearing masks. So it's Nadine Gill and Florian Stegborn. And this is a picture where we are together in the underground research laboratory in Mont-Terri, taking samples there. And Nadine, in her work, she mostly looked at bentonite alteration in the presence of corroding iron, so this evolution in the very near field. And in the beginning of a nuclear waste repository, there will be a so-called thermal phase where actually the clay is heating up due to the radioactive decay. And there are temperatures expected up to 100 degrees. And therefore, Nadine decided to study this alteration process at 90 degrees in batch type experiments. And also very important, we expect that after a certain while, there is no more oxygen in the repository. So this should be an anoxic corrosion. And what was observed is actually that the clay from the bentonite, which is mostly smectite, so there's active material, that this delaminates. So we lose actually this main diffraction peak of smectite, which, and the clay takes up a lot of iron, so up to 30 atom% iron. And after a long time, then here shown by this small peak here in these diffractograms for those who have a background in mineralogy among you, we see new clay minerals forming, which are more serpentine type clay, very iron rich and a different structure compared to the initial smectite, and also expectably different different characteristics. So like potential loss of swelling capacity or also decreasing cation exchange capacity could be something which could be expected. And so this was not the first study observing this transformation of the clay, but actually there are not many studies then going a step further in investigating how this altered bentonite would interact with radionuclide or would affect radionuclide transport. And therefore Nadine made a second type of study where she packed iron and clay, similar to the previous experiment, into a diffusion cell. And then this was saturated with water and altered. And there was an alteration going on also for 3 months, and again at 90 degrees centigrade. And then afterwards, she used this diffusion cell for diffusion experiments. And also post-mortem, she took out the clay from the cell and did adsorption experiment to see if the sorption properties of this clay have changed. And actually what we see that the diffusion of radionuclides here tested with H2O, like an inert tracer that is often used for this transport characterization, that the diffusion even decreases, likely due to some pore clogging of this, or this delamination, which leads to an intercollapse, and so some of this transport paths for the radionuclides in clay are blocked. And so we get a lower diffusion coefficient. And with respect to the sorption, we actually see, so here the line represents like the status before the alteration. And actually we see no tremendous change in the sorption capacity. The alteration, actually, it produces like these new clay minerals, and they have a slightly higher surface area. So we expect that the tiny increase that we even observe in the sorption capacity might be due to this. This is for cesium, for cobalt. We see for some experiments where there was really a very strong interaction with iron, we see a tiny decrease in sorption capacity, which could be like a competition reaction between the iron 2 and cobalt. But like I said, this is all hardly significant. So basically the sorption capacity is unchanged. And then a second study, we looked at the clay rock. And there we investigated opalinous clay of the so-called sandy facies, which is a kind of heterogeneous material, having not only clayey parts, but also sand lenses and various structures in it. And it's actually very complex material with heterogeneities on various scales, from the nanoscales with the very small clay minerals up to the facies or formation scale. And Florian first characterized this rock along drill cores on a very large scale of like 10 meters. And somehow categorized different types of layers there and found, for example, there one very pronounced layer, which he could categorize as a different subfacies of the rock. And on the other hand side, he also looked at the material at a microscopic scale. Here, for example, with an mineralogical analysis after an analysis of the rock with an electron microscope and then element mappings and then the mineralogical categorization. And actually there he found, if you look at a box of this with more than 600 micrometer side lengths, you find actually already a homogeneous mineral distribution. And if you look at it on a larger scale, then basically you look at a totally different thing, and you would need to have more than a meter that you average in order to find like a homogeneous appearance of the rock. So actually trying to quantify heterogeneity is just a very difficult task, and it really depends on the methods, how you look at the rock, and with which method or which parameter you consider during this investigation. This was just for the pure rock investigation with respect to mineralogy or just with the optical categorization. Then he tried to do the same also with respect to the sorption capacity. And that what he actually found is that when you look again at the microscopic details, you can see some heterogeneity in the sorption behavior. So this would be an image of the rock. Then again, the element distribution was measured and was transferred into mineral composition. And so here the green parts would be the more clay-rich parts. And clearly you see from the autoradiography image here that the clay-rich parts, that's where the cesium adsorbs. But as soon as you take a certain volume of this rock and you mill it, and so you get an average of these minerals and you measure the sorption there, you actually find already a very homogeneous behavior. So it does not really matter where you take these samples from. They all behave very similar. And if you want to make up any trend in there, then you can relate it to the clay mineral content of these elements. And these would be these bands which are displayed here. So that's basically model calculations that considers sorption only on clays. And this represents the data very well. But so actually, if you look at it in a different way, you could also say basically all the values independent of the clay content are rather similar. So if we say here 0.3 log units are not a rare case for the error of the sorption coefficients, then one could say that all the rocks behave fairly similar. So basically this means also here with the sorption experiment, we could show that finally, even though on a microscopic level we do observe heterogeneity, if we average over larger pieces of the rock, we find really homogeneous behavior. And now the next step will be to really also look into the transport properties, and this also from the microscopic to the macroscopic scales. For example, we had some very interesting samples from colleagues from Switzerland, and we did some micro CT investigations to check how far the diffusion behavior in these very small pieces of rock. So they are just 2 millimeters wide and about 1 centimeter long. And how far this depends on the distribution of different mineral phases in the rock. And finally, we try to transfer the knowledge that we gain here also to the very large scale. So this is in the Mont-Terri rock laboratory, where we installed a very large-scale diffusion experiment called DRD. So BDRD stands for the third borehole in the DRD experiment, where we installed such a setup as it's sketched here. And so now we will have soon we will inject radionuclides, and then they will diffuse into the opalinous clay in Mont-Terri so that we can study if the model parameters that we determine in the laboratory really can also describe the large-scale diffusion behavior as we observe it in an underground rock laboratory. And I think to summarize and conclude this part of the talk, so to get insights into the potential safety or safety risk related to radioactive waste storage in repositories in clay rock, we study sorption and diffusion of radionuclides in the near field, in the bentonite, and also in the host rock, clay rock. We aim at an holistic view of the whole repository, so not only including like the pristine substances that are there in the beginning, but also trying to include the evolution of the repository over time, and trying to study how this might impact the safety and the radionuclide transport. And also we try to take into account complexities like the heterogeneity of clay rocks, just to make sure that these do not really seriously impair the potential safety. And so far, I think based on the studies that I presented, we can say that even if we consider relatively unfavorable settings like altered bentonite or also this pronounced heterogeneity of clay rock, we can say that we found that this multi-barrier systems concept seems robust, and we did not observe any developments that might impair the repository safety over the long time scale. And that was it basically from my side, and I thank you very much for your attention. And because I did not mention any co-authors, I also, of course, want to wish all the people that were involved in the studies that I presented here. And of course, I also acknowledge the funding that was necessary to make this research possible. And with this, I hand over to Francesca, who will now give you more detailed insights into her research on radionuclide transport in crystalline rock.
Thank you, Frank. And thank you all for being here. So as Frank has introduced, now we go to the crystalline host rock concept. And as you see, as also Frank has shown previously for the concept of clay host rock, also here we have a multi-barrier concept. The nuclear waste is contained in a steel canister, for instance, surrounded by an engineered barrier system made of compacted bentonite and then the crystalline host rock. But now let's have a look at the mechanisms that are influencing the behavior of the radionuclides in a crystalline host rock. Or better to say, in this case, as you see in this scheme, the sequence of events that could cause the release and the migration of radionuclides in such a kind of repository. The diffusion, the matrix diffusion through crystalline rock is much slower than in clay rock. And in fact, the main mechanisms for transport of radionuclides in crystalline host rock will be the production of fractures that can be produced as a consequence of a major seismic event, for instance. Then the intrusion of low mineralized meteoric or glacial meltwater to reach the compacted bentonite barrier, which will then slowly saturate until also water will come in contact with the canister. And due to the corrosion of the canister, radionuclides may be released. after diffusing into the bentonite, they will reach the interface between bentonite and groundwater into the fracture. And here you see that bentonite is expanding into the fracture. This is one of the good characteristics of this clay rock, that it can expand up to 90% its original volume upon saturation, but at the same time there is erosion of the material and production of bentonite colloids that are particles whose dimension on the level of the nanometers make them stable and suspended into the solution, so they do not settle down. And here the interest in investigating both the migration and retention of radionuclides as dissolved species in the groundwater, but also their migration as species that are sorbed onto the bentonite colloids. So this is quite a complex system, and how do we investigate it in conditions that are as close as possible to the future geological repository conditions? You saw already previously that Frank will run experiments in an underground research laboratory in Switzerland that is called Mont-Terri. Well, we have also another collaboration with a different generic underground research laboratory at the Grimsel test site in Switzerland. And this is a facility that is managed by NAGRA, that is the National Cooperative for the Disposal of Radioactive Waste. And here you see the location of the Grimsel test site at 1,730 meters altitude within the R massif, and the laboratory placed at 450 meters depth into the granodiorite rock. And in this underground research laboratory, we run in situ radionuclide tracer test since more than 20 years in collaboration with NAGRA. This laboratory has quite unique features. One of them is the possibility to use radioactive markers, several radioactive markers, including actinides in the geosphere, so the presence of a controlled area laboratory, but also the presence of a mega packer system. You see this yellow tube that acts as a groundwater flow control. It prevents the groundwater to be in contact, to be at the atmospheric pressure, and that's why we can regulate the flux of groundwater for our experiment according to the needs. And this is a very important feature, and I will show you why in the next slides. And now let's also speak about the particularities of the Grimsel test site and the fact that the geochemical conditions in this granodiorite fractured rock, this geochemical condition resembles the expected conditions for a geological repository after intrusion of low mineralized meteoric water or glacial melt water, as we expect in the future. We have, in fact, reducing conditions, minus 220 millivolt of EH, an alkaline pH of 9.6, and a very low ionic strength of 1 millimolar. And in these conditions, bentonite colloids are highly stable and mobile, and therefore they can be carrier of radionuclide migration. How do we run these experiments? First, we start in our controlled area at our institute and in a glove box under controlled atmosphere of argon. In this case, we produce the so-called injection cocktail. We produce a cocktail of Grimsel groundwater, bentonite colloids, a conservative tracer, and several radionuclides. Here I have listed some actinides. And then we go to the Grimsel test site, and together with the colleagues of NAGRA, we perform the in situ test, injecting in a borehole of the inside of the granodiorite rock the radionuclide cocktail, and then extracting groundwater from another borehole after the cocktail has been in contact with groundwater inside of a fracture or a shear zone in which groundwater flow is carried on. And then the samples, the groundwater samples, are periodically collected and sent to our institute for different kinds of analysis, including radionuclide analysis. Of course, pH, EH, conservative tracers, concentration are continuously monitored at the injection and the extraction boreholes. And now I show you the results of an experiment that was carried out more than 20 years ago. And you will see why I do that, even though it's a very old experiment, but with very important results still lasting now. This was in the frame of the colloid and radionuclide retardation experiment. And in this experiment, the mega Packer system flow control, the yellow submarine I showed you before, was not yet in place. So the injection and the extraction of the cocktail and groundwater was done at very high flow rate. Laboratory experiments were carried out in parallel at our institute in order to investigate the sorption capability of the different radionuclides onto the fault gauge minerals of the fracture. What was inferred from the in situ experiment was that trivalent and tetravalent actinides, americium, thorium, plutonium, mainly migrate as sorbed onto clay colloids, the bentonite colloids. And their migration is somehow favored by the size exclusion of the bentonite colloids in the small pores of the fracture, so that the peak of their breakthrough curves arrives before that of the dissolved species that are composed by the uranium-6 or the uranyl neptunyl species. But what happened? Here you see, in this case, a summing up of the results of these experiments. An injection extraction rate of 5 and 150 milliliters per minute. Very fast. And you see a recovery, a quantitative recovery of all the radionuclides. So this tells me, for instance, that only the 30% of the injected americium stayed into the fracture because of sorption or filtering or other mechanism, but the most part, the 70% and even higher for the other radionuclides, was released, was collected again into the extracted groundwater. And so that was the idea to say, okay, let's go to conditions that are similar to those that we expect in a geological repository. And so let's decrease the groundwater flux. And this was then possible after the installation of this yellow submarine mega packer and flow control system. And a new experiment was carried out, and it was with 0.3 and 5 milliliters per minute injection and extraction rate, so 30 times lower than in the first experiment. And now let's look at the results. Look how different the recovery of the radionuclide tracers were. For instance, for americium and plutonium, we see a recovery, similar recovery, around 25-28%. That is also similar to that of the colloids, since we know that they migrate mainly as colloid-bound species, but extremely low recovery for neptunium and uranium. And this means that in the second experiment, with such a low flow, up to the 96% of neptunium was retained into the fracture. So this is a very, very good results, actually. This tells us about the retention capability of the system. But what is going on? Is there any slow release of these radionuclides? You know, we monitor this experiment for a number of days or for 1 month. What happens on the long run after days or months or years? We wanted to investigate that also in order to better understand what kind of mechanisms are involved into the retention of the several radionuclides. In the case of americium and plutonium, the low solubility of their species in these geochemical conditions, and also the colloid retention mechanism as their filtration and adsorptions in the fracture filling materials. In the case of neptunium, the reduction of neptunium-5 to neptunium-4 that is predicted by modeling solubility calculations, and then the surface sorption of neptunium-4, but also the sorption of neptunium-4 onto bentonite colloids and its possible then mobilization. And for uranium, that is in this pH and EH condition of the Grimsel test site, is stabilized as uranium-6 as carbonato uranyl calcium uranyl carbonato complex this reduced recovery would be due to isotopic exchange with naturally occurring mineral phases or surface sorption of aquatic uranil species. Okay, but does it stay like that? What happens on the long run, as said before? Look at these plots on the left side. The red squares, they represent the concentration of americium, plutonium, neptunium, uranium, only uranium not yet, as they were measured with ICP-MS, a very sensitive analytical technique. But after 25 days from the starting of the experiment, the concentration of the radionuclides were not anymore detectable with ICP-MS. We were below the detection limit of this technique. And therefore, we used another technique which has a higher sensitivity, it's called accelerator mass spectrometry. And here you see that with this technique, we could investigate the much lower concentration of the radionuclide tracers in the tailing, in this case up to 236 days. So we increased of an order of magnitude our capability of analytical observation, but also before the arrival of the peak of the radionuclide tracers. And also, just in this case, this is an example for uranium-233, AMS offers particular advantage because of the fact that this technique is able to suppress molecular and in some cases atomic isobaric interferences. Here I give you an overview, a comparison of the total inventory of several radionuclide tracers that were used in situ experiments. You see technetium-99 up to 10 to 16 atoms, americium-241 10 to 13 atoms. And the detection limit of AMS, that would be the levels of 1 million, 3 million atoms for technetium and 10,000 atoms for the actinide. So we are at the level of sub-femtogram, attogram, or micro, or in some cases nano becquerel of activity. And I just wanted to point out this and also to tell you very briefly about AMS and its sensitivity, because we use this technique in situ test and also laboratory test in order to investigate long-term behavior of the radionuclides. And here you see the scheme of two AMS mass spectrometry facilities with which we have collaborated in the last years for experiments run at the Grimsel test site. This was the former facility at the Technical University of Munich, which was recently decommissioned, and this is the Vienna Environmental Research Accelerator of the University of Vienna. The main reason for the high sensitivity of AMS is the fact that we can think about that as two mass spectrometers, one first here and the second here, that are linked by an electrostatic tandem accelerator, which functions as a background suppressor, as a isobaric molecular dissociator. And that's why we can run such sensitive analysis because, for instance, in the case of uranium-233, we are not affected by the background of thorium hydrate, and similarly for technetium analysis. But now let's go to the results of the second experiment. I showed you already that with this ultra-sensitive analysis, we saw that there was a clear signal of the 4 radionuclides tracer before the arrival of the cocktail of the new experiment. And then we were thinking, what can it be the origin? We could exclude laboratory contamination background. And then we were thinking, hey, in the past years, starting 2002, there were 3 other experiments that were carried out, and they used similar radionuclides, Neptunium-237, Americium-243, Plutonium-242. But then we saw that there was one experiment in which not only uranium-233 was also used, but 2 different isotopes of americium and plutonium were used. So 241 instead of 243, 244 instead of 242. So we thought, okay, let's analyze again the samples and see whether we find these very old tracers from more than 10 years ago. And indeed, we found them. And here you see extremely low concentrations of plutonium-244, americium-241 at the beginning, before the arrival of the new cocktail experiment. And then after that, we see a peak in their concentrations that corresponds to the peak of the freshly injected radionuclide tracer, and then also a tailing. So this is a clear signal of radionuclides remobilization from the previous experiment of more than a decade before. But we wanted to be sure, and so we did isotopic analysis. We compared, you see in this plot, the horizontal lines represents the isotopic ratio 241, 243, 244, 242 in the cocktail, in the radionuclide cocktail of the new experiment. And here we have these ratios as determined into the groundwater samples. And here you see that they are consistent with each other only in correspondence to the arrival of the peak of the breakthrough curves. Before and after, they are different. So this was a proof that actually the constant levels we analyzed at the beginning were signal from the previous in situ test. Then here we had a predominance of the radionuclides from the new experiment, and here possibly a remobilization of americium and plutonium from the fracture filling materials because they sorbed onto the bentonite colloids freshly injected with the new experiment, and then a mixture of the 2 sources with the long tailing up to 8 months from the starting of the experiment. So this is an example of how we, with ultra-sensitive analysis, can also unexpectedly run a decades-long experiment and observe in situ condition the long-term behavior of the radionuclides. And now I give you a last example. I go back to the bentonite diffusion. Also, you saw the examples of the experiments brought by Frank in the first part of the presentation. In this case, also radionuclide diffusion was investigated in compacted bentonite that was emplaced inside of a borehole intersecting the shear zone at the Grimsel test site. Here you see a scheme of the experiment. Here would be placed the so-called long-term in situ test, and here around you see 3 smaller boreholes that were used for collecting groundwater samples and monitoring the possible release of the radionuclides. And here you see a scheme of the experiment that is longitudinal to the wall of the tunnel. And here you see the compacted bentonite rings that are surrounding a carbon steel mandrel. And here the violet rings are those spiked with several radionuclides. The experiment was lasting 4.5 years, during which the bentonite was saturated by groundwater flowing through the fracture, here depicted in orange. And during this time, groundwater samples were collected at 2 sampling boreholes that were 5 centimeters distant from the bentonite source. So what we collected here was mostly groundwater that was in contact with bentonite and bentonite pore water. And so we wanted to analyze the diffusion, the possible diffusion at ultra-trace levels of radionuclides through the bentonite, but then also their advective transport, so the near field release within 5 centimeters. And the radionuclides were technetium-99 and several actinides. And here I show you the results related to technetium-99. And here you see this near field release of technetium-99 as compared to the release of the AGA conservative tracer. You see already that the 2 curves, they do not resemble each other, but there is a peak for technetium and then it decreases up to 3 orders of magnitude. And then with these few chosen samples, we could see a long tailing of almost uniform concentration. This was an indication of in situ reduction of technetium-7, the mobile phase of technetium, the pertectinate, to technetium-4, as predicted also by thermodynamic calculations. But very important, you see, the comparison between the recovery, or better, the near field release, compared to the emplaced inventory. For the conservative tracer, we are in the percent levels, so 0.4 0.0337, but in the case of technetium, the recovery was several orders of magnitude lower, so only 8.5 times 10 to the minus 5 of the originally emplaced technetium found its way out of the bentonite and then in the groundwater. So in this way, I wanted to point out how with our research in underground research laboratory and also the ultratrace analysis, we can observe directly in situ, in repository relevant condition, the behavior of the radionuclides. And here we have seen evidence of retention in the granodiorite fracture and an ultratrace continuous release, also through reversible reaction within the fracture and desorption, also mediated by the bentonite colloids of radionuclides over decades. We have seen how there is an inverse correlation of the residence time of the radionuclide cocktail and the radionuclide and colloid recovery, and so how kinetics of redox or isotope exchange reaction can strongly affect the retention of the radionuclides. New in situ radionuclide tracer tests are also being performed in order to support these findings. Also, we have seen proof in situ of the different mechanisms of migration of the radionuclides for americium and plutonium as colloid-borne species. At the same way, they can be dissociated from the colloids and absorbed directly onto rock surfaces. And also the mechanism of retention for uranium as isotopic exchange and surface sorption, and the reduction of the pentavalent neptunium to the tetra strongly sorbing species. And for the bentonite in situ experiment, we saw how the ultratrace analysis allowed us to see a very low release of technetium-99 from the system. And so Frank and I have been showing you how it is important a deep understanding of the geochemical properties of the radio elements, not only in the field of environmental science, but especially in the safety of nuclear waste disposal and decommissioning, and how with in situ radionuclide tracer test and our collaboration with Mont-Terri and the Grimsel test site, we can gain experience in long-term monitoring of radionuclide propagation near a repository. We can evaluate long-distance migration of the radionuclides, but also the long-term geochemical behavior of the radionuclides at the engineered barrier system and host rock boundary. And now I go to the conclusion of this talk, and I thank the Colloid Formation and Migration Project, an international project led by NAGRA at the Grimsel test site, our German partners, and the Federal Ministry for the Environment, Climate Action, Nature Conservation, and Nuclear Safety for funding. And of course, I thank all our collaborators and students, and we thank you for your attention.
Thank you very much for this very in-depth and detailed presentation about a fascinating topic, and it's really great to see research and science advancing on those topics that are maybe not often or not always talked about in the nuclear sector, but of course we all understand this research is much needed for the whole nuclear sector. I'll shortly just give an overview of the upcoming webinars, if I manage to change the slides. Yes. So the Education and Training Working Group will be celebrating its 10 years this year, and this is the opportunity for us to organize a live panel discussion from our experts and policy group meeting that will happen next week in Korea. So you will find here there is the link, and on the GIF Public website, a link to directly join the webinar and the panel distantly on the 15th of October. So the times are in Korea times, 4:30 in the afternoon till 6 in the afternoon. But all the detailed information is on the GIF Public website. And we continue our series of webinars in the upcoming months. So in November, we will have a webinar about the safety of SFRs. In December, an overview of nuclear energy advanced modeling and simulation tools to accelerate the development of advanced reactor systems. And in January next year already, we will have a presentation, a webinar about the history of nuclear reactors development. I'll pass that very quickly also. It's just, and then so you will find this presentation and these indications on the website, but this is an overview of where to find the webinars on the new GIF Public website. So the webinars are all stored under events and resources, and when you arrive on the events and resources, you go to webinars, and then you have the full list of webinars. You can also, by clicking on the here text that is in caps here, you can have a list in a table of all the webinars and access them all. Unfortunately, I think we're running out of time, so I don't think we will be able to take the question and answers, and I'm sorry about that.
Yeah, I'm sorry to thank you so much, Frank and Francesca. Today I'm in Texas, so I really have to run to Tamu. But thank you very much, everyone. You have the on the presenter slides the email address of Frank and Francesca. Feel free to send them your question if you have questions. Again, the webinar is recorded and it will be archived on the GIF portal as well on the YouTube channel for GIF Education and Training Working Group. So thank you, everyone. Thank you, Frank, and thank you, Francesca, and thank you again, Alexei, to host this webinar. Thank you, everyone. Have a good day.
Thank you. Have a good day.
Thanks.
Thank you. Bye-bye. Merci. Thank you. Bye-bye.